So, before we get into binomial specifically, we're going to talk about the types of questions we can expect to see when we look at this section here. So, binomial and geometric models occur whenever the same chance process is repeated several times. So we're often interested in whether a particular outcome does or doesn't happen on each repetition. Okay? So we're going to have binomial and geometric distributions that we're going to use to calculate different probabilities. Each one has its own separate conditions and properties as well. So here's one example of a time we could use a binomial or geometric. So if you wanted to test whether someone has ESP, choose one of the 4 cards at random, ask the person to identify the card without seeing it. Do this 50 times and see how many cards the person identifies correctly. Okay? So all you're doing is choosing one of the 4 cards, you're having them tell you which card you chose, and you're just doing that same process over and over and over again. So we just have a random process being applied numerous times. Okay? Another example, in the game Pass the Pigs, a player rolls a pair of pig-shaped dice. On each roll, the player earns points according to how the pigs land. If the pigs land on opposite sides, which is called a pig out, the player loses all their points. So how many rolls on average will a player get before pigging out? So there we're saying if we just roll those pig-shaped dice over and over and over again, how many times could they do that before they get this pig out, which would be them up there laying on opposite sides. So with the binomial and geometric random variables, we're looking at a repetitive process. We're doing something over and over again for a certain number of trials. Okay? Now, binomial and geometric, like I said, have their own properties. They have their own conditions. So today, we're going to focus only on the binomial. So a binomial random variable counts the number of times the outcome of interest occurs in a fixed number of repetitions. So in this definition, the 2 pieces that are probably the most important for identifying whether you have a binomial distribution or not. We are looking at the number of times a specific outcomes occurred, or the number of times a specific outcome occurs. So basically we're looking at the number of successes that we can expect to see. The other big piece is that we have a fixed number of repetitions. So we're going to do our chance process a specific number of times and stop. So we're going to roll the dice 10 times and be done. We're going to flip a coin 25 times and be done. So we have a fixed number of trials that we're going to try out. Okay, that's the big thing with binomials. So we're looking for the number of outcomes that occur out of a fixed number of repetitions. Those are the 2 big key things to take away from that definition. Now, one of the things you have to be able to do is take a scenario and determine whether you have what we call a binomial setting. That means, are we dealing with an actual binomial random variable? So in order for a binomial random setting to occur, there are 4 conditions that must be met. And on any problem where they ask if you have a binomial setting, you need to make sure you comment on all 4 conditions. So yes, it's binomial because it does these 4 things. Or no, it's not binomial because it violates this specific condition. So to be binomial, it has to satisfy every single condition. To be something that's not binomial, it only has to fail 1. Okay? So, the first condition, there can only be 2 outcomes to your repetitive process. Either you succeed and get what you were looking for, or you fail and you don't get what you're looking for. So most often when we're dealing with these, you're going to see the terms success and fail as the two outcomes. So given a chance process, there can only be two specific outcomes. Either you get what you're looking for or you don't. The second condition, the trials must be independent of one another. So as you continue to do your repetitive process, each iteration of that repetitive process must be independent from the one previous. So flipping a coin, I flip the coin, record what it has. I take the coin and flip it again. Then I take the coin and flip it again. Every time I flip the coin, it's an independent trial. Rolling dice. Every time I pick up the dice to roll again, I'm performing an independent trial. Whatever happened before isn't going to affect what happens later on. Okay? So it must be independent each time you do your repetitive process. The next time must be independent of the previous time. The number of trials, which we denote with the letter N. So the number of trials for your process must be fixed in advance. So we're not doing something until a certain outcome occurs. We are doing something a specific number of times, and that's it. So I'm going to flip my coin 20 times and be done. I'm going to roll my dice 10 times and be done. So there has to be a fixed number of trials at the onset. And then your fourth condition, the probability of success, which we denote with a lowercase p. The probability of a success must be the same for each trial. So each time I go back and do whatever process I'm applying, so whether it's flipping a coin, every time I flip the coin, I have a 50-50 shot at heads or tails, whichever one happens to be a success. Okay? So every single time, every single trial has to have the exact same probability for success. So when all four of these conditions are met, then we have what's called a binomial setting. Okay? So again, in order to be a binomial setting, all four conditions need to be met. For it not to be binomial, only one has to fail. So when you're trying to, or doing these types of problems, you either need to show that all four are met, or you need to show which one fails. Which one doesn't it follow to make it a non-binomial setting. So we're going to look at three settings here and determine if they're binomial or not. Setting number one. Genetics says that children receive genes from each of their parents independently. Each child of a particular set of parents has a probability of 0.25 of having type O blood. Suppose these parents have 5 children. Let the random variable x be defined as the number of children with type O blood. Okay, so this is our scenario. We need to determine if this dictates a binomial setting. So what's the very first condition that needs to be met? 2 specific outcomes. Do we have 2 specific outcomes here? Yeah, what would a success look like? The kid has type O. What would a fail look like? Kid does not have type O. Now, don't get confused with the fact that there are more than 2 blood types. You can be type O, type A, type B, and type AB, right? There are 4 different types of blood types out there, but in our particular setting, we are only concerned with whether the kid has type O or not. Does that make sense? So there are only 2 outcomes. Success, they have type O. Fail, they don't. Okay, so that's condition number 1. So we have that. Condition number 2 was Trials must be independent. So that means each time they have a kid, that kid's genetics has to be independent of the previous. So do we have that? Yeah, in fact, this one actually specifically mentions that. It says genetics says that children receive genes from each parent independently. Okay? So the genetics happens independently. So that's condition number 2. Condition number 3. Are there a fixed number of trials? 5. They're having 5 kids. That's my fixed number of trials. Okay? So I have that. And then the last one, the probability of success is the same for each child. So every time they have a kid, does the probability that they have type O stay the same? Yes, it would. It's always going to be a 25% chance. So all 4 conditions are met. Would this be a binomial setting? Yes, it would. So you would say, yes, it's binomial, and then you would list those 4 conditions and how it applies to this particular setting. Okay? Let's take a look at the next one. Shuffle a deck of cards. Turn over the first 10 cards one at a time. Let the random variable y be the number of aces you observe. So if we start through our conditions, condition number 1 is what? Only 2 outcomes. So in this case, we have only 2 outcomes. Yeah, we either get an ace or we don't, right? So we're concerned with finding aces. So either we get an ace or we don't see an ace. Are the trials independent? No. Why not? Because once I flip a card, what's happening? I'm changing the possibilities for future cards to be an ace or a not, right? So I'm changing my probability as I flip. So I could actually use that as either of the 2 conditions where I can say they're not independent, or I can say that the probability for success doesn't stay the same throughout. Every time I flip a new card, I'm changing the probability of getting an ace. Does that make sense? So either one of those would be satisfactory for just saying this is not a binomial setting because those conditions fail. Okay? How about this one? Shuffle a deck of cards. Turn over the top card, put it back in the deck, shuffle again. Repeat this process until you get an ace. And let W be the number of cards required to accomplish this feat. So condition number 1. Are there 2 outcomes? Yeah, either we get an ace or we don't. So we're okay there. Would we be independent in this particular scenario? Yes, we would be. If I'm going to take a card, but then I'm going to replace it and reshuffle, that means my probability is going to stay the same all the way throughout. So the probability of an ace stays the same throughout this process. Do I have a fixed number of trials? No. In this case, they say draw until what? Until you get an ace. So in this case, we have no idea how many times we'd have to do that, which means we don't have a fixed number of trials, so this is not a binomial setting. So 3 of our 4 conditions were met. Where we failed is the fact that we don't have a fixed number of trials. We're saying do it until something happens.
Could there be any situation that it would the trial would the probability would stay the same, but then it wouldn't be independent? Because those go run through the same thing.
No, yeah. They pretty much get to the same idea. I don't know why they split it into 2 separate. But yeah, if they're independent, then the probability should be staying the same. If their probability stays the same, they are going to be independent. So yeah, those kind of go hand in hand. So as soon as you've shown that one works, you've shown the other one kind of works as well. All right, so we're okay with that? Identifying binomial settings. All right, so if we have a binomial setting, we are able to use our binomial model to determine different probabilities or look at the distribution of outcomes within our setting. So, if we're looking for the number of successes in a fixed number of trials, we can use the following model to calculate how many successes we expect to see and with what standard deviation. We can also use the model to predict probabilities. What's the probability that in this number of trials I see this many successes? Okay, so the key pieces here, you need to know what each of the different variables stands for. P is your probability of success. X is just your generic random variable definition, so X, Y, whatever they define their variable as. Now, when you look at how you define your variable, it's very important. We are looking for the number of successes in our fixed number of trials. So that N stands for the number of trials. Now, the other thing you may want to add here, P is the probability of success. Q is the probability of a fail. So when we look at these settings here, we have a P and a Q in there. P stands for the probability of success for our given scenario. Q is the probability of a fail. Now think about the relationship between those two probabilities. If P is the probability of success and Q is the probability of fail, what should be true about those two probabilities? They should add up to 1. They're going to be complements of each other. So one of the things your book might do, if you're using your book to kind of help as you're looking through the different problems and things like that, they don't necessarily use the term Q. The way they write that is using that complement rule, and they'll write their formulas using the 1 minus P. Okay? So take the probability of success, 1 minus that would be your probability of fail. But I feel that the formula itself is a little bit easier to work with if we have two different variables that we're identifying here, so P and Q. Now, before we get to this probability model here, we'll come back to that. Expected value, standard deviation. These are two things you need to be able to calculate and interpret for a given setting. When I ask for the expected value of X, what am I actually asking? The mean. I want the mean number of successes. So when you see that expected value or they ask for the mean, what they're asking is, in this setting, how many successes should we expect to see? So if I'm flipping my coin 10 times, how many successes should I expect to see when I do it 10 times? So if I was to run one setting, flip my coin 10 times, I get a result. If I flip it 10 times again, I get another result. If I flip it 10 times again, I get a different result. What we're looking at is, if I were to put all those results together, what's the average value? What's the average number of successes I can expect to see overall? So when you look at this expected value here, you're looking at the number of successes you expect to see. Okay? So how many successes should you see within that N trials? Now, standard deviation is the same as it's always been then. So we know how many we expect to see from our mean, or our expected value. The standard deviation is going to tell us the typical distance we are away from that mean. So I expect to see 7 heads out of this scenario with a standard deviation of 1.2. So typically I'll be about 1.2 away from my number of successes. Okay? So standard deviation means the same as it's always been, the typical distance from the mean.
Do we need to memorize that formula? Or will you be able to like have it?
This one here?
Yeah.
You will probably want to, like some of the multiple choice questions will have that formula. So let's say, what's the probability? And instead of actually just working it out to the actual probability, it's going to leave it in this notation. So you do want to understand what that formula looks like, yeah. So yes, I would. The way we calculate our probabilities, we're not necessarily going to use this very often. We're going to use our calculators here in a little bit. But they might leave it in this form, so you still need to know kind of what we're dealing with. Okay? All right, so with this binomial model, mean is calculated by taking the number of trials times the probability of success. So how many total trials are we working with times the probability of success. That's going to tell us how many successes we can expect to see. Okay? Standard deviation is taking the square root of the number of trials times the probability of success times the probability of fail. So you use all three pieces there. Okay? So as far as calculating goes, you just need to memorize these two formulas. Make sure you understand how to calculate the mean and the standard deviation for a binomial setting. Now, probability. This formula looks very complicated. Okay? Now, what we're working with here, this NCX. Sometimes you'll see this notation written like this. So you got a set of parentheses, and then they have this n over x. They're saying n choose x. This is calculating the combinations. You guys dealt with combinations and permutations back in pre-calc, yes? Okay, so it's probably one of your tougher units. Combinations and permutations, they come back. Now, the good news here is you never have to worry about whether you use combinations or permutations. With a binomial setting, you're always going to use that NCR or that combination function. Okay? So, basically, what this tells us, if I was doing 10 trials and I wanted to see exactly 4 successes, okay, so I'm running 10 trials of something and I want to see 4 successes overall. What this first part of the formula does is it calculates how many different ways that can happen. So if you think about that, 10 total scenarios, 10 total trials, 4 successes. Those 4 successes might be the first 4 I run. They might be the last 4. I might get 1 success, 1 fail, 1 success, 1 fail, alternate until I have 4, and so on. There's lots of different ways for it to occur. So this NCX calculates the total number of ways to get that many successes. Okay? So basically, you take the total number of trials, choose the number of successes you want to see. Now in your calculators, go ahead and get those out. And KJ, these will probably be a little different for you, so you'll have to look that stuff up a little later probably. All right, if you want to do this NCX here, so let's say we had 10 trials and we wanted 4 successes. Okay, so if I want to do 10 choose 4 in the calculator, you're going to type in 10, go to your math key, over to PRB or PROB, depending on what type of calculator you have, what operating system. And it should be around the third option, you see NCR. So you choose that option, and then type in the number of successes you want. So on your screen, 10C4 should look like this, 10 NCR4. Everybody got that? So when you're doing this choose notation, you go into math, over to the PRB or PROB, and then you choose that option for NCR. Okay, so type in the number of trials, type in the NCR, type in the number of successes you want. Okay, Now, the rest of the formula should be pretty straightforward. So from here, my next step is to take the probability of success times the total number of successes, or to the number of successes that I want to see. Okay? Think about this. If I was calculating, let's say I just have 6 trials, and I wanted to have 2 successes, for instance. Well, if I want to calculate the probability that of getting 2 successes in 6 trials, that probability of success could be my first 2, which means the rest all have to be Q's. I've got the probability of success times the probability of success times the probability of fail times the probability of fail, and so on. But like we just talked about, there's numerous ways for this to occur. So that's why we have this first part, the NCX. From there, I know I need 2 successes. I need 4 fails then in that case. So not only are the P and the Q complements of each other, but the number of outcomes are complements of each other as well. So I take P raised to the number of successes I want to see, times Q, the probability of fail, to the number of fails that I expect to see. So if I have 6 trials and I want 2 successes, that means I'm going to take P to the 2 and Q to the 4. So I need 4 fails if I have 2 successes. Okay, so when we're looking at this formula, you can simplify it down a little bit. Probability of success to the number of successes. Probability of fail to the number of fails. If you think of it in those terms, rather than this whole P to the X and Q to the N minus X, it becomes a lot easier to work with. P raised to the number of successes, Q raised to the number of fails. Okay? Then the only other thing you have to worry about is just getting your NCX at the beginning to account for the different ways that these can happen. Okay? So, blood type. Let's go back to that first example we had that was a binomial setting. So we already established this idea of getting type O blood as a binomial setting. So each child of a particular set of parents has a probability 0.25 of having type O blood. Suppose the parents have 5 children. So first thing, how many of the children can the parents expect to have type O blood? And with what standard deviation? So if I want to let X be the number they're going to be the number of children with type O. What they're asking us to calculate is the expected value. So how do we do that? N times P. So how many total trials do we have? 5. There are 5 children. What's the probability that they have type O blood? 0.25. So how many total children should we expect to have type O blood? 1.25. Okay? And again, this is an expected value, which means it's an average, so don't get hung up on the decimal part of this. Obviously, in a setting of 5 children, we cannot have 1.25 of them have type O blood. Okay? So the 1.25 is simply an average. If we had this same setting over and over again, and we had couples having 5 random children over and over, on average, we would expect to see 1.25 kids with type O blood. Okay? So there's our expected value. If I want to calculate my standard deviation, then the formula says take the square root of N times P times Q. So, in my square root, N was 5, P 0.25, Q would be 0.75. So if there's a 25% chance of having type O, you have a 75% chance of not. So if you plug that in your calculator, that for me? 0.97. Okay, so we should expect to see 1.25 kids with type O blood, standard deviation of 0.97. So if we were to look at typical families with this same exact scenario, we'll normally be off by about one child from that 1.25 expected value. Okay, so mean and standard deviation, pretty straightforward. Just calculate based on the formulas. Okay. If we want to calculate the probability that exactly 3 of the children have type O blood. So in notation, if we're letting x equal the number of children that have type O blood, what we're trying to answer here is what's the probability that x equals 3. So what is the probability that we get exactly 3 kids with type O blood? So from our formula, we would do that in CX. So how many total children are we looking at? 5. CX, x would be the number of successes we want to see, which is 3. Times, what's my probability of success? 0.25. Raised to the third, we want 3 successes. So raised to the third. Probability of fail, 0.75. How many fails should we expect? 2. Okay, so in your calculators, 5 NCR3 times 0.25 to the third times 0.75 squared. So you can do this pretty much all at once in your calculator. And when you're doing this, I would suggest making sure you have your parentheses in as well, just for added measure to make sure you have what'd you guys get? 0.08789, so on, right? So one of the things, make sure you know how to type this in. So 0.08789, so we can go ahead and go to 0.088, okay? So this tells us that there's approximately an 8.8% chance that 3 of the kids in this setting will have type O blood. Okay with that? Okay? Now, I'm going to show you guys how to do this on your calculator so that you don't necessarily have to use this formula every time. And you're going to see why we don't want to use this formula every time coming up on the next example here in a second. But I want to kind of start getting you guys practicing with this right now. So, if you want to calculate a binomial probability on your calculator, you can go into what's called the distribution menu. You're going to hit second, vars. So the vars key is right by the arrows. So hit second, vars. And what you're going to see on the screen right away should be like normal PDF, normal CDF, inverse norm, inverse T, things like that, right? So second vars gets you into your distribution formulas. Now, what I want you to do is scroll up. So from that first main screen, scroll up once. And now what you should see at about your second or third option, you should see a binom PDF and a binom CDF. Does everybody see those? Okay. So binom PDF, binom CDF. These are the 2 distributions you will utilize if you're working with a binomial setting. Now, the binomial PDF. PDF is when we're looking for a specific number of successes. Binomial CDF is utilized when we're looking for a range of successes. So when it says in 10 trials, what's the probability that you get exactly 6 successes? Exactly 6 means a very specific number of successes. That's a PDF problem. If it said in 10 trials, what's the probability of getting more than 6 successes? Now we're looking for a range of successes. That could be 7, 8, 9, or 10. So that's going to be a CDF problem. Okay? So for our setting right here, which would we choose? PDF. We're looking for exactly 3 kids to have type O blood. So go ahead and select that option. Now when you select that option, do you guys all come up with a menu to fill in some blanks? Does anyone go straight to the screen and have this looking at it? Okay, so if you get that, I'll get to you here in a second. We'll talk about what you need to plug in here. For those of you with the menu, just follow what it's asking for. So the first thing it asks for is the number of trials. So those of you that are looking at this on your screen right now, that's going to be the first thing you type in. So how many trials are we looking at for this setting? 5. So you're going to type in 5. For those of you with the menu, just hit enter to get to the next blank. For those of you with this, you're going to type in a comma. All your arguments are going to be separated with a comma here. The next thing it asks for is P. P is the probability of success. So the probability of success here would be 0.25. So that's the next thing you type in. That's your next argument. And then the last thing it asks for is the X value, which is the number of successes, in this case, 3. Okay? So at that point, you should hit paste, and this is what you should see on your screen. So everybody, regardless of whether you have the menu first or not, this is what your argument should say. So number of trials, comma, probability of success, comma, number of successes. Okay? And now when you hit enter, what do you get? Same that we had before, right? So about 0.088. So that's another possibility for calculating your probabilities. Rather than going through this entire formula here, you can type it in using that binomial PDF or binomial CDF. Now, if you choose that option, you cannot simply write your answer down. You need to actually write out what you used. So you need to show that you used binomial PDF or binomial CDF. You need to give me the arguments you plugged in. Okay? So you need to actually show me exactly what you did. You're not off the hook because you're not choosing the formula to work your problem out. You have to tell me what you used because there are still lots of different ways to make mistakes. Maybe you typed in the wrong N value. Maybe you typed in the wrong X, or maybe you typed in the wrong P. So I can see where your mistake happened rather than just you have a wrong answer, so I have no idea whether you knew anything about what you were doing. So every single problem, whether you use the formula or whether you use your calculator, you have to show me exactly what you're typing in. Everyone understand that? Okay, that's homework related and quiz and test related. All of them have to always have everything worked out. Okay? So now, let's find the probability that fewer than 3 children have type O blood. Now, if I were going to be using my formula, I would have to calculate the probability that 0 kids have type O, plus the probability that 1 kid has type O, plus the probability that 2 kids have type O. So my scenario here calls for every possible scenario where less than 3 children have type O blood. So I can do that as 3 separate formula probabilities and then put them all together, or we can use the calculator to shorten our workload. So in this case, since we're looking for a range of success or the values, we would say what's the probability that x is less than 3, which means instead of PDF, this time we'd want to choose CDF. So one thing to note here, when you're using CDF on your calculator, that always tells you less than. So if your probability is less than, then CDF is going to give you exactly what you want. If your probability is supposed to be greater than, what are you going to have to do with this binomial CDF? Subtract it from 1. So you're going to calculate it based on the calculator and then subtract from 1. So less than, we're good to go. Now, I go to binomial CDF. Okay? My number of trials hasn't changed. I still have 5 kids. My probability of success hasn't changed. It's still 0.25. But now I have to tell myself, or I have to tell the calculator where I want it to cut off at. So I want fewer than 3 kids. So where do I want it to stop calculating? At 2. If I wanted 3 or less, then I would include 3 in my calculations. But since this says fewer than 3 of the children have type O blood, we can't include 3 in our calculation. We want to stop before we get to 3. So our number of successes here is going to be 2. So this is what I would need to see on your homework or on your quiz or on your test. Binomial CDF, 5 total trials, 0.25 for success, stop at 2. Okay? So now if you calculate that, what do you get for a percentage? What does your calculator say? 89.6%? Okay, so you get about 0.896, 89.6% chance. Everyone okay with that? Okay, real quick. If they had said, what's the probability that 3 or more have a type O blood? So the probability that 3 or more have type O blood. Now in this case, we're looking at a greater than scenario. I can't do greater than on the calculator. So if I'm looking at the probability that x is greater than or equal to 3, I need to look at the complement. So if I want 3 or more, my complement, what I don't want would be 2 or less, right? So I would calculate the probability. I would do this binomial CDF. 5 trials, 0.25 for success, 2 successes. Okay? So I need to look at what I don't want and then subtract from 1. So here, I would be doing 1 minus the binomial CDF and then whatever else I'm plugging in. So anytime you get a greater than problem, you have to think carefully. If this is what I actually want, what is what I don't want, because that's what I need to calculate in the calculator, and then subtract that value from 1. So it's a little more involved when you have to do a greater than problem. Okay? Real quick, 10% condition. Now, our entire problems are set upon the idea that those 4 conditions are being met for our binomial setting. Now, when sampling from a finite population without replacement, we can sometimes run into a problem with independence. So binomial trials have to be independent. If they're not, we cannot use a binomial setting. So if the assumption is violated, if we don't have independence, we can still proceed as long as our sample is less than 10% of the population. So if we have reason to believe that the trials are not independent from each other, we can still call it a binomial setting if the number of trials we're using is less than 10% of the total population. Okay? So in some cases, you might have something that's not independent, but the sample is small enough that we can still proceed because we're less than 10% of the overall population. All right? Last thing, the binomial model, as you increase the number of trials that you run, simply becomes more normally distributed, which means you could use the normal model to calculate. However, we won't use the normal model very often because the calculator takes care of all of that. Okay? The one thing you do need to know, though, I would write it down and take a picture real quick. In order to use a normal distribution, the number of successes and the number of fails that you expect to see have to be larger than 10. So if you take n times p and n times q, both of those results have to be at least 10 to proceed with the normal distribution. Okay? So then there's your there are your problems. You might want to at least get a picture of this because I don't know when the blogs are going to be back up.
They're already up.
Are they? Because mine wasn't earlier.
Physics they were during second round.
Okay.
It wasn't during advanced.
Because I tried during advisement and mine still wasn't up, so I'll have to try again. But just in case, get this written down or a picture snapped. Start working through these problems tonight.